Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 38, Triple Counters or Asynchronous Counters of Chapter 7, Counters and Registers of the course Digital Logic Design or Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in Digital Logic Design, however, there are many books available. In Chapter 7, we start covering Introduction to Digital Counters, Ripple or Asynchronous Counters, Binary Ripple Down Counters, Binary Ripple Up Counters, or Up-Down Counters, and other Ripple Counters. What is a digital counter? A digital counter is a sequential network or finite state machine that generates a sequence of numbers. This sequence may be and may be not in a binary or decimal order. So for instance, a counter can count in a binary order from 0 to 15, which is 0, 0, 0 to 1, 1, 1, 1, or it could count in down sequence from 1, 1, 1 to 0, 0, 0, or it could count in irregular or in non-binary sequence like add numbers, like even numbers, like any sequence that we wish. It depends on the application. Let me assume a counter counts 0, 2, then 3, then 7, then back to 0. So a counter can count in any sequence you wish. A counter may count in another sequence, another example like 1, 7, then 5, 6, then back to 0. So in any sequence, as long as it counts, so in any sequence it may change state and we can design the counter accordingly. The counter consists of a number of flip-flops and may have combinational network. You may see a ripple counter without a single gate. The maximum number of states or counts is 2 to the power k, where k is the number of flip-flops. Applications of digital counters. Digital counters are used in applications such as direct counting. For instance, you have a parking garage and you would like to count the number of cars in this garage. So you will have an up-down counter. Any car goes in, you will increase the counter by 1. Any car leaves the garage, you will decrease the counter by 1. Also, counter is used in digital clocks and frequency counters, time, distance, and speed measurements. In waveform generation, you can generate a sinusoidal waveform or a triangular waveform using counters. They are also used in sequential addressing, ATD converters, frequency divider circuits, Christmas decoration circuits, and variety of other applications. Typically, they find applications in digital communications, digital signal processing, digital computers, and digital control systems. So they are indeed extremely useful. And to learn how to design them and how to analyze these counters are extremely difficult, extremely important, I meant. So extremely useful to learn how not only to design and to analyze. There are specific definitions in counters, in digital counters. Modulus. The maximum number of counts is known as modulus of a counter. So we call the counter modulo 16 or mod 16 counter that counts 16 states from 0, 0, 0, 0 to 1, 1, 1, 1, or 0 to 15 in decimal. In general, mod n counter counts n states where n is any integer. Now divide by n counter is equivalent to binary mod n counter. It means we will count binary sequence. So for instance, if we say divide by 16, it is modulo or mod 16 counter. And we call it mod 16 because divide by 16 because the 4 outputs will have, the first one will have the frequency divided by 2, the frequency divided by 4 for the second output, the frequency divided by 8 for the third output, and for the most significant output, the frequency divided by 16, where f is the frequency of the input clock pulse. Now also we have something called asynchronous counters and synchronous counters. Counters are classified according to their design as ripple or asynchronous counters or parallel or synchronous counters. In synchronous counters, all flip-flops are triggered with the same clock simultaneously at the same time, while the flip-flops are not triggered exactly in step with the input clock pulse in an asynchronous counter. Often you find the asynchronous counter, the first flip-flop triggered by the clock pulse, while the second flip-flop triggered by the output of the first flip-flop, and so on and so forth. Up versus down counters. Counters are also classified according to their operation as up counter, down counter, or up-down counter. A counter counts in forward direction is known as an up counter, like 0 to 1 to 3 to 4 to 5. A counter counts in down direction or reverse direction is called down counter, like starting from 7, 6 down to 0. A counter counts in which counts in both directions is called up-down counters or forward-backward counter or reversible counter. So you may have a counter is like an up-down counter, which will serve many applications. Now let's look at the ripple asynchronous counter. In a ripple asynchronous counter, the first flip-flop is triggered by the input clock pulse X, while each other flip-flop is triggered by the transition that occurs in the previous flip-flop. A chain of uncascaded flip-flops form a mod 2 to the power n binary ripple counter. So if we take the first flip-flop, flip-flop 0, will be triggered by the clock X, the output Q will trigger flip-flop 1, this is the output Q0, the output Q1 will trigger flip-flop 2, and the output Q2 will trigger flip-flop 3. Here you will have the most significant bit will be Q3, and the least significant bit will be Q0. So this is my output. Now, as you see, the clock is X, okay? Changes between 0 to 1 at the negative edge, because all these flip-flop are negative edge triggered. Q0 will be, flip-flop 0 will be triggered at the negative edge, and you see Q0 will change from 0 to 1. And this will go on, actually, that Q0 will be changed from 0 to 1 at every negative edge of each of the following pulses. However, the Q0 will trigger flip-flop 1. So at the negative edge of Q0, flip-flop 1 will change from, the output of flip-flop 1 will change from 0 to 1, and so on and so forth. The same thing at the negative edge of Q1, flip-flop 2 will be triggered and change state, change from 0 to 1, okay, accordingly, and so on and so forth. At the negative edge of Q2 will trigger flip-flop 3, and the output Q3 will be changed from 0 to 1. And will remain 1 until it will be triggered again with the next negative edge, which is right here, okay? So this is what will generate the binary sequence that we are seeking. We have 0, 0, 0, which is the first binary sequence at Q3, Q2, Q1, and Q0, 0, 0, 0, 1 till 1, 1, 1, 1, 1. And in the next cycle, we will start with 0, 0, 0 again. Okay, so this will show you how simple that the ripple counter will work to generate all these frequencies. For instance, if the frequency here 1000, you will get 500 here, you will get 250, you will get 125 here, and you will get 1/2 the 125, which is 62.5 cycle per second here. So as you see, this is divide by n. This is what the name divide by n. came from because of the frequency, the change in the frequency. F divided by 2, F divided by 4, F divided by 8, and F divided by 16. So, with this in mind, this is give me a ripple up count, not down count, up count. Now with the ripple up count, we can generate the state table and the state graph. Okay, and this is how shown. So if we start with the state 0, with the clock pulse 1, we'll go to state 1. With the clock pulse, we go to S2. If there is no clock pulse, I remain in the state. Okay, I will hold until we have a clock pulse. Okay, and so on and so forth. So we have really 16 states from S0 to S15 and back to S0. And accordingly, we will have the present state S0 to S15. And the next state as X0 will remain at the same state. But S0 at X is 1 will go to S1. S1 at X is 1 will go to S2. And this will be the next state table. Now with this table, it's with the binary state assignment. If we assume S0 to be 0, 0, 0, 0, so you will have 0, 0, 0, 0 at X0 will remain as 0, 0, 0, 0. At X is 1, we will go to 0, 0, 0, 1, and so on and so forth. So this will show you how really the state graph and the state table been really driven for this simple ripple counter. We have 16 states, and we have the corresponding 16-row truth table and the corresponding truth table, state table with a state assignment. And those we call them binary state assignment. It means S0 will be the 0, 0, 0, 0, and S15 will be 1, 1, 1, 1. As we will see later on, those state assignments for any machine could be chosen by a specific scientific analysis, and it's too early to talk about it now. Actually, we are coming there soon. However, the ripple down counter, the same thing actually with one change we do here. The first flip-flop FF0 will be triggered by the input clock pulse X. For the second flip-flop 1 will be triggered by Q0 prime, and FF2 will be triggered by Q1 prime, and FF3 will be triggered by Q2 prime. Okay, so this is the only difference here. And here we will have the X, the clock pulse. We have a 16 clock pulses shown here. And Q0, Q1, Q2, Q3 initially all ones. So at the negative edge, I will move from 1 to 0, 1 to 0, 1 to 0 for Q0. Then at the negative edge of Q0 prime, but it is here actually shown the positive edge, and the reason we see the positive edge because the complement of Q0 will have a complement signal, which is not shown here. So the trigger here is occurred at the positive edge of the clock. So we will generate 1 to 0. Then at the positive edge, the next. So Q0 triggered at the negative edge of the clock. I do apologize. At the negative edge, because still this is a negative edge, but Q1 is triggered at the positive edge of Q0 or the negative edge of Q1 prime, because we are using the clock Q1 prime. So you find actually this is triggered at the positive edge. So I have 1, 1 change to 0 at the positive edge of Q0. The same thing here. I have 1, 1, 1 at the positive edge of Q1. You will trigger flip-flop 2. And at the positive edge of Q2, you will trigger flip Q3. So all of the flip-flop are negative edge trigger. Since we are taking the clock from Q0 prime, okay, so and we are looking at the complement of Q0 prime, which is a Q0. So you see the triggering here at the negative edge of Q0 prime to the positive edge of Q0. And And accordingly, we generate the binary sequence in the down binary sequence from 1111. Then we have 1110, then 1101, then 1101, 1100, then 1011, and so until we reach 000. Then we start with the next cycle. Now, to design an up-down counter, what we need to do the following. We need the flip-flop 1 to be triggered by Q0 if it is an up count, and by Q0 prime if it is a down count. The same thing with the flip-flop 2. The same thing with the flip-flop 3. Flip-flop 3 needs to be triggered with a Q2 when we have an up count, and with a Q2 prime when we have a down count. So we define a signal Y, an input signal. When Y is 1 is up count. When Y is 0 is down count. And the clock pulse for these flip-flop 1, 2, and 3 will be actually according to this Boolean function, which is YQ or Y prime Q prime. If Y is 1, I'm choosing a Q. If Y is 0, I'm choosing Q prime. As simple as this. So it is 2 AND an OR gate, okay, between the flip-flop. So I have Y Q0 or Y prime Q0 prime for the first one, Y Q1 or Y prime Q1 prime for the second flip-flop, and Y Q2 or Y prime Q2 prime for the third flip-flop. And those two AND gates, and we have Y and Y not. And by doing that, we generated an up-down counter. And this circuit works very nice. Now, other ripple counters. We may need to build other ripple counters like decade counters or BCD counter, and we can do this by eliminating number of states. And often we use the preset and the clear of the flip-flop to preset the counter at specific state. For instance, if I like to, in this example 1, to design a decade counter will count from 0 to 9. But once you hit 10, which is 10, 10, 10, 10, or just take Q3 and Q1 to an AND gate to generate a 0 and clear all the flip-flop. So we go back to state 0, as simple as this, okay? 2-input NAND gate, okay, and we take the output to every clear of every flip-flop to reset the counter to all zeros. And this will generate a decade or binary coded decimal counter. The same thing if we need mode 5 ripple counter. A mode 5 ripple counter, I will design a mode 8 ripple counter, which is 3 flip-flops. Once I hit 5, which is 1, 0, 1, I will take a Q2 and Q0 to an AND gate and clear the counter to the S0 state or 000 state. And this will allow me to design a mode 5 ripple. So I will see 0, 1, 2, 3, and 4, which is, but when I hit 5, which is 1001, the counter will clear fully, and I go back to state 0. The same thing with mode 7. Once I hit the number 7, I will clear this counter will count from 0 to 6. So once I hit 7, which is 111, we take them to 3-input NAND gate, and you can take them to the clear pins of each flip-flop. And this will generate a mode 7 ripple counter. This will be the end of the ripple asynchronous counter. And I would like to thank you so much. Please subscribe by clicking on the blue circle. And sincerely, Dr. Hassan. Hopefully to see you soon in the next lecture. Bye.